Welcome to the Astrophysics Talk series of Istanbul University Observatory. Today our speaker is from Indian Institute of Science Education and Research, Beri, and she will be giving a talk on fast timing and broadband look at neutron star X-ray binaries with ASTROSAT. So it's your turn, Aru. First, we thank you for accepting our offer to you to give a talk in this series. Thank you, and it's your turn.
Sure, thanks. Thank you. Good morning, everyone. And I would like to sincerely thank all the organizers for inviting me to give this talk. So as already mentioned, the talk will be based upon fast timing and broadband study of neutron star X-ray binaries with ASTROSAT. So to start with, to give a brief introduction about the systems which we talk about or cover during this talk. So they are X-ray binaries. And as the name suggests, they predominantly emit in X-rays. And if you look upon the geometry of these systems, so they are a binary star system where one of the star here is a compact object or a dead star, which is often a neutron star or a black hole or a white dwarf star, which is because of its strong gravity, it's accreting matter, or matter gets transferred from the companion stars sitting close to each other. So these both stars are revolving around each other around a common center of mass. So as we understand, the angular momentum of the incoming matter is extremely high, so it does not directly impinge onto the compact object which is sitting somewhere at the center here. So it forms the circular disk or the circular radii along the circumference of this compact object. And this is known as an accretion disk. And this is an efficient machine in terms of generating X-rays from these mass transfer process. So the energy released, the gravitational energy released is in the form of X-rays, what we observe with space instruments like launched by NASA, ESA, or ISRO. So even if we say that these are X-ray binaries, but it doesn't mean that they only emit in X-rays. There are different bands of electromagnetic waves which is being covered in their emissions, and the emission regions and the processes responsible for that emissions are different. Although predominantly what we observe it is in X-ray. So for say we have jets emerging from these objects, which is observed in the radio band, and we do observe optical emission, which is from the outer layers of the accretion disk. So second important thing which we should explain this talk is because this talk is based upon ASTROSAT results. So what is ASTROSAT? ASTROSAT is the first multi-wavelength X emission launched by ISRO, and it's one of the very important mission in Indian history, which includes 5 payloads. And when it says multi-wavelength, it means that it covers from all the way from UV to X-ray band and X-ray at very higher energies. So this artist impression on the bottom top left shows the impression of an ASTROSAT, how it looks like. And in the red boxes observed here on the top are the major instruments which are on board ASTROSAT, which is large area X-ray proportional counters. And if you're familiar with X-ray astronomy history, you might be aware of that in the past we had an excellent instrument, which is Rossy X-ray Timing Explorer mission by NASA, which was also led to a lot of discovery space in terms of studying variability in. So now after RXT, LAC-PC is and in the similar energy band or the energy range. LAC-PC is also probing into the variability features in X-ray binaries, since these X-ray binary systems are highly variable objects. They show large variabilities in terms of the changes in their accretion disk and the accretion mass accretion rates. And then we have soft X-ray telescope. So this X-ray telescope is similar to the SWIFT instrument, where we have X-ray telescope on board SWIFT, and it works in the similar energy ranges. from 0.3 to 7 keV, and as name suggests, it's an imaging instrument. And while LAC-PC is a proportional counter, non-imaging instrument, and then we have CCTI, which is again extending to very hard energies, which is above 15 keV or so, and can extend all the way to 200 keV. And this is excellent instrument for observing hard X-ray emission from X-ray binaries. And in addition, it has opened a new discovery space in understanding polarization from different hard X-ray polarized sources like CRAB and GRBs. So then we have scanning sky monitor. So this is some sort of all sky monitor in the onboard ASTROSAT, which monitors all the transient phenomena which is taking place in the sky. So it basically scans the sky and records all the new outbursts or new transients which are coming from these exciting objects. And what makes us multi-wavelength is the UWIT instrument, which is there shown in yellow here. This instrument, as the name suggests, it extends to the UV band, and hence one can probe into multi-wavelength characteristics of these objects using all the 5 payloads of the. In this talk, we'll be focusing on the neutron stars as a compact object, and when we talk about neutron stars, they do have a lot of diversities in itself. So we will be broadly covering the classification, which is based upon the magnetic field strength of the neutron stars. So neutron stars can have high magnetic field, which can be of the order of 10 to the power 12 to 13 Gauss. And in these cases, the neutron stars are often known as stars. And then when we talk about the low magnetic field neutron stars, then the range here is missing, but the order of magnetic field measurement is of the order of 10 to the power 8 to 10 to the power 9 Gauss. In that case, they are known as low magnetic field neutron stars. Even if I say low and high magnetic field neutron stars, if we compare it with the magnetic field strength of the Earth, it is huge. So the first part of the talk will be covering low magnetic field. The magnetic field is of the order of 10 to the power 8 to 10 to the power 9 Gauss. So the important aspect of understanding these neutron stars. So first question which arises is, why are we interested in these systems, or what makes neutron stars so fascinating for us to study? So these objects are extreme or are natural laboratories that can allow us to probe into dense equation of state. So we might have heard of experiments like Large Hadron Collider on Earth, which helps us in probing in discovering exotic particles but at higher temperatures. But now when we talk about neutron stars and the core of the neutron stars, we actually have supranuclear densities, which are existing at very low temperatures. And we cannot attain those densities at those temperatures in any laboratories on Earth. Hence, they are natural laboratories to understand the which is it is composed of and how we can do that. So when in the case of low magnetic field neutron stars, in a binary system, when it accretes matter from the companion star, the matter actually spreads onto the surface of the neutron star. And when the right conditions of temperature and pressure have been achieved, it undergoes an unstable nuclear burning or a thermonuclear runaway. And in observations, what we observe in X-ray is this sort of profile in the intensity profile. So on the y-axis, we have the intensity, and on the x-axis, we have the time variation. So this profile, from this profile, as you could see, this is the counts in kilo units, so kilo counts per second, and then time is of the order of a few tenths of seconds, which means the profile, intensity increased to a very high intensity, to a very high level within a very short interval, and then there shows an exponential decay. So this profiles or these such signatures observed in X-ray light curves or X-ray intensity profiles is known as thermonuclear X-ray bursts. And they are one of the very few tools by which we can actually try to understand or constrain mass and radius of the neutron star, and which when probed can understanding about the equation of the state or the composition of the neutron star. So for mass and radius measurements, one has to study these thermonuclear X-ray bursts. And these, so from the observational point of view, we believe ideally these bursts emit more like a thermal black body spectra. So when we say thermal black body, it means that if we do the time slicing of each segment in this burst, oh, was I muted all the time?
Yeah, it was, you were muted for a few seconds, so you can go on now.
Okay, so did I miss anything? I'm not sure because I was like going into.
Yeah, just last maybe 10 seconds.
Okay, so I was talking about thermonuclear X-ray burst, and here when we believe it's a black body emission, so which means we can understand the spectra using a black body models, and from a black body models we can actually estimate your radius and the temperature from the normalization which is coming from the spectrum. And so from the Stephen-Boltzmann law, one can estimate the radius, which can come from this formula given here. So as infinite script infinity, because it's neutron stars are away from us, so we are observing them from distance. And this is like a local or a neutron star intrinsic parameters of temperature and the radius, which are actually modified with the gravitational redshift and the color correction factor, which I'll talk about next slide. So as you have seen in the previous slide, when we have to estimate the mass and the radius of the neutron star in this case, we have modified it with the gravitational redshift and the F factor, which I mentioned as a color correction factor. So these are actually the uncertainties which propagate when we do neutron star radius measurements using these tools. The first uncertainty is about the composition of the neutron star's atmosphere. So ideally, we believe that it's a thermal black body emission, but then there can be a hot electrons existing surface of the neutron stars or close to the atmosphere of the neutron stars that can actually lead to the upscattering of the thermal emission from the neutron star, which means your thermal black body can be modified in that case. So this is some sort of uncertainty and goes in our assumption when we perform the spectral fitting using just a simple black body model. Another uncertainty parameter was a gravitational redshift. Again, this is a parameter which is based upon various assumptions and estimated based on various assumptions. So another uncertainty is, of course, the distance measurements, because for measurement of the distance to these objects, one has to have a precise measurements based upon now we have Gaia, which can allow us for obtaining distance estimates. But when we compare distance estimates of known neutron star X-ray binaries with the previous measurements, we see there are discrepancies upon previous measurements and the measurements made by Gaia. So now all those sort of discrepancies can actually mitigate when we do radius measurements for the neutron stars. So another, the last or one of the other uncertainty which propagate in the neutron star radius measurements is the partial surface emission. So we assume that the neutron star spreading all the matter on the neutron star surface was uniform, but it cannot be an ideal case. It can be only a few patches of the neutron star are burning, and that leads to the thermonuclear emission. So go into calculations of the neutron star radius. And this is an example study what we have performed using ASTROSAT data of one of the source 1636. And here we have performed time resolved spectroscopy during the thermonuclear X-ray burst, which is shown in the top panel here, the burst profile as we observed in the ideal profile shown here. So you see a fast rise and then there's an exponential decay. And then each bin or 1 second bin was actually fit with the black, the conventional method we said. And then we actually used a modified method, which is known as FA method. And what we did is in the second method, which is FA method, is we are assuming that there is some contribution of the persistent emission, or which is the emission just because of the gravitational release, but not because of the thermonuclear runaway, is also contributing to the burst flux. So when we include that parameter, what we observe is that the FA, which is a sort of a constant parameter, which we include to take care of the contribution of the persistent emission, it showed large contribution close to the peak of the burst. Such studies have been done in the past also, that which hints us that black body assumption is not an ideal assumption for measuring the neutron star radius, and modified ways of estimating the radius should be taken into account. And the green patches here we'll be talking about later in my talk are the patches where we actually detected burst oscillations. So this is the again same source, Fourier 1636536, and this is very well studied neutron star X-ray binary system. As I mentioned, there was in the past RXT, which was a dedicated mission for studying these neutron star X-ray binaries, and so it has like thousands of observations available in the archive. So very well studied source. And when ASTROSAT was launched in 25th September 2015, soon after that, this source was observed during the performance verification phase of the ASTROSAT. And when we were studying the observations made by ASTROSAT, what we found intriguing was this sort of profile in the burst. And if you see that their time difference between the two bursts is of order of few minutes. So it's known as X-ray triplet, and these are rare triplets. So usually we find isolated thermonuclear X-ray burst, and at some times we also see which means two thermonuclear X-ray bursts separated by less than 45 minutes. So the classification of short recurrence time burst is based upon the time difference between the two bursts. So if your time difference between the two bursts is less than 45 minutes, they are known as a short recurrence time burst. And in this case, the wait time between the second and the third burst was just 5.5 minutes. And as thermonuclear X-ray burst has been extensively studied in the past with RXMM integral. So this burst catalog is well maintained by MinBar, which is maintained by Monash University. And we looked at the MinBar for observing how many times X-ray triplets have been observed in this particular source. So if we look, and including other sources as well, as when we say it's a rare triplet. So here it's a list of sources which indicates that number of triplets observed in different sources are only few tens. And while if you look at the MinBar archive, it's including several thousands of thermonuclear X-ray burst being studied so far, which means that which indicates that triplets are indeed rare. And when we look at about the wait times observed in during the burst in 1636, we found the shortest wait times observed during triplet was of the order of these minutes. And when we compare it to the wait times what we recorded with ASTROSAT, it is like, it suggests that it is one of the shortest recurrence time observed with ASTROSAT. Thanks to NuSTAR, after ASTROSAT observation, there we found another observations with NuSTAR of the same source. And well, while we were studying this NuSTAR observation, we found another rare triplet in the long observation made by NuSTAR. And when we estimated the wait times here, then the wait in the first and the second burst here was the order of 3.8 minutes. Now this suggests that after 5.5 minutes, 3.8 minutes is the shortest time recorded as a wait time for this particular source. Now, when we talk about short recurrence time bursts, there are several possibilities being discussed about the origin of this short recurrence burst, that what causes this short recurrence time burst. One of the proposed hypotheses is a waiting point in the nuclear chain reaction, because as these, eruptions from the neutron star surface are believed to because of the thermonuclear runaway. So it is suggested that there could be a point in the nuclear reaction network when there is a wait point, and after that waiting point, the next series of nuclear reaction takes place, and hence the second burst come into the picture. But there are several speculations about this hypothesis of the waiting point in the nuclear chain reaction. Very recently, work done by numerical simulation based upon numerical simulations by Keek and Hager in 2017, they suggested that there could be leftovers from the previous burst. So during this thermonuclear runaway, it is believed that some sort of nuclear reactions takes place. It can be RP process, or it can be some sort of chain reaction like CNO or something, which can lead to these bursts. So not all the fuel from the previous burst was burned, and which means there are some leftovers of the matter which is being accreted. And this matter is actually transported to the ignition depth via convection. And that can lead to the profiles which were simulated here and shown here of a triplet. And these profiles, if you look at the triplet, the times between the wait times between the burst actually matches what we usually observe during observations. Even the intensity or the luminosity being measured during thermonuclear burst matches with what we observe in observations, but the profile is equal to what we observe in reality. So I'd say you see these sort of eruptions or some sort of a bumpy behavior within the burst profiles. And if you look at the observational profile, it was very flat. I mean, it was flat between two bursts. And similar profile has been observed in the past also. So for example, say this is an integral profile observed with integral observatory, and for Equalus X1, a different source, the triplet has been actually the same sort of profile. There's no bumpy behavior observed. So the generated profiles are not identical to what we observe, but then the time scales and the luminosity measurements actually match with the observations, which again suggests that there are some things which are to be still incorporated to get the identical or to match the observations. The third hypothesis could be that there could another model which says spreading layer model based upon spreading layer of the accreted matter. And this proposed model can explain some observation points of the short recurrence time burst. But then again, there are some sort of limitations in this model as well, which I will discuss soon. Before that, I will talk about another interesting observation which we found in the burst profile of the thermonuclear burst. So in the literature, we found with the integral data of a particular source, Fourier 1728 in this case, Kazawa et al. Have found, so integral is an instrument which works in very high energies, high X-ray energies. And when they looked at the burst profile at very hard band, like around above 40 keV or so, they found a dip in the, at times when there is a peak in the thermonuclear X-ray burst. And then they explained this bump or the dip in the burst profile at very high energies based upon the electron cooling effect. So they believe that there's some sort of electron cooling. Because of that, the flux from the hard X-rays is lost, and it adds to the soft X-ray flux. And this is how they explain their observations. Now, the advantage of ASTROSAT to study this hard X-ray emission is that it has large collecting area, and it has very good time resolution. So even with a single X-ray burst, we can actually probe into such features in the hard energies. So what we did was we took all the bursts, and for independent bursts, we actually tried to generate the energy resolved burst profile in hard energies. So in this case, 30 to 80 keV. We did observe the dip here, which is like consistent or at same times when the peak of the burst is observed. But when we do proper corrections like dead time correction, etc., of the burst, then the dips disappears. So which means that dip was not real. It was some sort of instrumentation correction which causes that dip. So at least for ASTROSAT observations of thermonuclear X-ray burst, we did not find any signatures of the dips in the hard energies. Then important feature, which is thermonuclear burst oscillations. So what are thermonuclear X-ray burst oscillations? So when we study this burst, in addition to time resolved spectroscopy, from the timing point of view, we can actually observe the spin frequency of the neutron star, or measure the spin frequency of the neutron stars by detection of these pulsations during the burst. And these are not always observed. One has to basically use more careful techniques to understand the power density spectrum of these burst profiles to detect such signatures. And how these burst oscillations are originated, it is believed that they are because of the asymmetric brightness patterns during the thermonuclear X-ray burst of a spinning neutron star. So these temperature asymmetric brightness patterns can lead to some sort of oscillations during the burst, which are at the spin frequency of the neutron star. Thus, one can measure the spin frequency of the neutron star if you detect a burst oscillation. And these burst oscillations can be observed either during the rising phase or the decay phase of the neutron star. So 1636 again, it's a well-known studied source with RXT, so it's a sign from RXT data points, and on the y and x-axis we show hard and soft colors. So by hard and soft colors, basically it's some sort of a model independent way to understand the spectral state of the source. So by spectral state, I mean because it's accreting matter from the companion star, which means the accretion disk is dependent upon the mass accretion rate. The accretion disk can go closer to the compact object if your mass accretion rates are higher, and it can away from the compact object if the mass accretion rates are lower. And based upon that, different physical processes can lead to like predominance of some emission over the other. So some here mean hard X-ray emission over the soft X-ray emission. Usually X-ray astronomers associate any emission above 10 kV as hard X-ray and any emission which is below 10 kV as a soft X-ray emission. So this is like without incorporating any assumption in the model, we are just looking at the data which is being collected by the instrument. You basically take hard X-ray over the soft X-ray, which is known as hard color. And if you take vice versa, soft over hard, then you name it as soft color. So by this time independent way, you can actually see in what sort of spectral state it was in, whether it was in a soft state where the soft X-ray emission was predominating over the hard X-ray emission, or if it was in a hard state where the hard X-ray emission was predominating over the soft emission. So in the data points shown in red are from ASTROSAT. So we have just aligned on the hard color diagram obtained with RXT where the ASTROSAT observations lie. So from these, one can actually make out that observation 2 and 3 were taken during the soft spectral state, while observation 1 and 5, 6, and 4 were during the hard state of the source. So this is the detection of burst oscillations, and what we found with oscillations made with ASTROSAT is you can see spectrum. There's a peak which is observed at almost 5 sigma detection level, which is around 581 hertz in this case. So this is the spin frequency of the neutron star of this particular system. And then we did the dynamic power density spectrum. By dynamic power density spectrum, we actually studied the evolution of the frequency of this feature with time. So you can also see at what times the power was higher. So as you can see here in the grid here. Apart from that, this was the first time when we did the very detailed timing study of thermonuclear X-ray burst with ASTROSAT. And how that detailed timing study was done, we studied the frequency evolution of this burst oscillations. Then we calculated how the frequency fractional RMS amplitude was varying over time. We measured radius, and then we did a further study to understand the phase lags in these observed during these burst oscillations. So as this was one of the interesting example from the study, where we see that there are high fractional amplitude observed during the rising phase, which is obvious, or which is almost consistent with what we have seen in the past. That during the rising phase of the thermonuclear exciburst, the fraction amplitude actually is higher, and then it shows um, a decay or a decrease in the fraction amplitude close to the peak. And then we observed a very high amplitude fractional values at a decay phase. This is something which is not always found, but has been seen in a few bursts in the past with RX-T. So these high amplitude high amplitude decay profiles or decay oscillation profiles during, along with high amplitude rising phase oscillation, was something very interesting which we found in our observations. So how to explain these high amplitude oscillations? For rising phase, the explanation for this is very based upon the hot spreading layer model, hotspot spreading layer model, which explains the profile. But for the decay phase, for the low amplitudes, one can understand from the surface modes or the exciting modes or R modes which are on the neutron stars, that can lead to this low amplitude. But for the high amplitudes, there are several uncertainties of what the origin or what causes this high amplitude decay phase oscillations. So perhaps in our case, we propose that it could be like both cooling peak model and the surface modes are at work. And then there is a frequency drift, as you could see from the frequency evolution or the dynamic power density spectrum. It is actually based upon the angular momentum conservation. So in the beginning of the observed frequency is less than the spin rate, and later the spin frequency, as the layer settles down, it increases, or the spin frequency of the neutron star. Then we observed some sort of soft lag, which means that whether the hard X-ray emission or hard X-ray photons were arriving us, or soft X-ray photons were arriving us faster. So this is known as lag profile. So when we did this phase lag study, what we found was a soft lag, and the soft lag can be easily explained by the Doppler shifting. So how it is explained, it could be like the hotspot which is emitting hard X-rays is along our line of sight. So that's why hard X-rays are approaching us first compared to the soft X-rays. So as I mentioned in the beginning, you observe the during the rising phase high amplitude which decrease over time. So this is like some sort of concavity which we observed in the profiles, and which is fit, indicating that they are consistent with the spreading hotspot model. And the fractional amplitudes actually showed us an increase in the increase in energy, which means that higher energies had higher fractional amplitudes, and which could be explained because of the high background contribution at lower energies, while at higher energies the fractional amplitude is not affected by the persistent emission, which acts as a background here in this case. So from all that detailed timing study of thermonuclear exciburst, what we found was thermonuclear exciburst oscillations were detected during both hard and soft spectral states of the source. And we observed short recurrence time burst profiles, which could be explained by the spreading layer model. However, there is significant improvement needed to incorporate various features in the burst, short time recurrence burst. So one of the missing feature or missing parameter is that they are based upon the assumption that the matter is only spreading meridionally, or latitude dependence is there. However, the radial component or radial velocity component is being missing in the model. So which is an important factor, because radial velocity is also another contribution which can lead to a contribution to the short recurrence time burst profiles. So it has to be incorporated to be matched with observations. Burst oscillations are in good agreement with the proposed models. However, to probe into the energy dependence of like phase lag to understand it more better, one has to incorporate or demand simultaneous observations with NICER and NuSTAR, because advantage of incorporating NICER is NICER also is excellent timing resolution instrument in the space launch in the space now launched by NASA, but it covers soft energies which are like around 0.3 to 12 keV. So at those energies, there is a contribution from the absorption along the line of sight and so on. So once we incorporate or do this time star, which we can actually get more consistent, more rigorous values of your phase lags, and which can help us in understanding the models way better, or can lead to the more improvement in the current models. So coming to the second part, where we had probing into the accreting millisecond exapulsars with ASTROSAT. So this is another class of neutron star exabinaries where we observe millisecond pulsations in the power density. And these millisecond pulsations are not during the due to thermonuclear runaway, they are because of the gravitational energy release, or and then they are actually at the spin frequency of the neutron star. So these systems actually are kind of excellent systems to understand a bridge between thermonuclear exaburst oscillations and to study this accreting millisecond exapulsars. So we studied this source XJ1748 with ASTROSAT, and most of the accreting millisecond exapulsars known so far are transient objects. So this is the profile with the obtained with Swift XRT, shown in red, overplotted over MAXI data points, and the shaded regions actually show the times when ASTROSAT observation was made. So the good part was that we actually found a simultaneous observation taken with XMM Newton, which was overlapping in times with ASTROSAT. So that actually helped us in getting a real broadband coverage of this particular source. With timing study using ASTROSAT LAX-PC data, what we found was 442 Hertz oscillations in the power density spectrum, and this is the pulse profiles what we obtained by doing the timing study, and the pulse profiles were actually fitted using two sinusoid functions with the two harmonically related periods. So this is like a resultant rate profile which was obtained by two sine curves fitted together. And the fractional amplitude measurement was of the order of 0.5 Hertz, 5%, which is not very high in this case. But it's always difficult to detect pulsations in accreting millisecond exapulsar sources. Another thing, or advantage of using ASTROSAT, as I already mentioned, you can get a broadband X-ray spectrum coverage, which can help us in getting insights into the various physical processes causing or contributing to the X-ray spectrum. So for example, on the top, we see there is an accretion disk, a compact object sitting here. So there can be contribution from the reflection of the disk. So the timely emission can get reflected from the accretion disk, and then we can observe some reflection components in the X-ray spectrum. These reflection components can be based upon the abundances in the accretion disk, which is like, say, if your accretion disk is rich in iron atoms, then it can lead to an emission line in the X-ray spectrum, which is in the form of iron. Or you can always observe, you may observe a Compton hump in the hard X-rays, which is the reflection component in the X-ray spectrum. So there in the bottom panel, which we observe a broadband coverage where we have black, green, and red. So red from LAX-PC, and black is from Neutron, XMM Newton, green is from FXT. So this is actually is a broadband coverage for all the three instruments being studied, used for this particular study. And when we did a broadband spectroscopy of the source, we found a highly ionized presence of very highly ionized accretion disk, which was best fitted using the reflection models, which is like silver CP in this way. In this case, so the ionization parameter was extremely high, of the order of 3200 centimeters per second. So apart from that, we also observed iron abundance in the accretion disk. So this was an important thing. Of course, with the broadband X-ray spectroscopy, one can estimate the flux values, and that those can allow us to estimate the magnetic field of the neutron star in this particular actually estimate the upper limit to the magnetic field, which was of the order of 1.6 into 10⁹ Gauss. So this is the upper limit to the magnetic field strength of the neutron star in this particular system obtained with ASTROSAT. Coming to the same type of sources, accreting millisecond X-ray pulsar, again Saxray 1808 was observed with ASTROSAT, which were our observation as a target of opportunity observation. We mark here the ASTROSAT observation being made. Again, similar study was done where we found pulsations at 401 Hertz. And this study is still ongoing, and we are almost about to write a paper on it based upon our energy dependence and spectral study done so far. The last part of my talk will be covering the high magnetic field neutron stars. Just wanted to know how I'm doing with time.
You have time, no worries. You can go on.
Okay, thank you. So when we talk about high magnetic field neutron stars, unlike low magnetic field neutron stars, your matter is channeled onto the poles of the neutron star by the magnetic lines or forces. So here in this case, you see a neutron star with a magnetic field axis, then you have, rotation axis, then you have magnetic axis, and then you also have a line of sight. So the misalignment between these three axes can lead to X-ray pulsations, what we observe, and then they are known as X-ray pulsars. So when with ASTROSAT, we have observed various X-ray pulsars, but in this talk, I'll be focused only on one important source or source in the which was observed with ASTROSAT was a BE X-ray binary, and one of the first galactic ultraluminous X-ray pulsar observed with ASTROSAT. And also, so it's a BE X-ray binary star, which is a high mass X-ray binary system. Now again, neutron star X-ray binary systems, or rather X-ray binaries, are classified as low mass and high mass X-ray binary systems based upon the mass of the companion star. If your mass of the companion star is less than solar mass, then they are called low mass X-ray binaries. When you have a mass of the companion star greater than 8 to 10 solar mass, then they are known as high mass X-ray binary systems. And then they are further classified in high mass X-ray binaries like BE X-ray binaries or supergiant X-ray binaries, again as the name suggests, based upon the companion type. So here BE star is there, and these are important class of X-ray pulsars, high mass X-ray binary systems, where we do observe two types of outburst. One is type 1 and another is type 2 outburst. And in the bottom, you see type 1 outburst. So the difference between type 1 and type 2 is type 1 is very periodic in outbursts. So they are separated in the two outbursts are separated by a orbital period of the system. So it's basically from when the neutron passage or comes closer to the BE star. So it accretes a large matter from the circumstellar disk around the BE star and leads to an outburst. While the type 2 outbursts are not very recurrent, and they are also not like periodically separated in time. So 2 outbursts, your recurrence time is unknown. It can actually take few decades also to get to see another outburst in the same source. So what is the motivation of studying these transients or these type of outbursts in these BE X-ray binaries? So one of the important motivation is to understand the luminosity dependence of different features observed in observations. So for example, say, you can extract, because these are X-ray pulsars, so you estimate the pulse period from the power density spectrum, and then you generate the pulse profiles. And by studying pulse profiles, one can actually understand the accretion geometry, because what happens is in the stars, when matter is channeling onto the poles of the neutron star, you see it's forms like a cylinder on the poles on top of the neutron star. And these cylinders can be totally filled or can be half empty or half filled or mostly empty based upon the mass accretion rates, which means luminosity. So again, if it's completely filled, then it is believed the flux or the radiation is coming from the close to the neutron star, like this, if you see, observe here. So in that case, your pulse profiles are expected to be more like a sinusoidal or simpler in shape. While if your mass accretion rate is lower, then what happens is it's the radiation or the X-rays which is coming from the hotspot actually propagates from this column or accretion column, which we call it as the cylindrical formation is known as accretion column. So this emission is coming from the column. Because it is coming from the column, which means it has mass also, the column, because it says matter coming from the companion star. So it can interact. The radiation coming from that cylinder can actually interact with different matter or at different heights. The density profiles and the homogeneities are, there are inhomogeneities in the accretion column, which can lead to the modification of the radiation, which means now the simple shape of the profile will be modulated by different effects. So we can expect different shapes of the pulse profiles at different intensities. And this is what an example profile shown here for a particular source 1901, where different profiles are observed at different times, which is given here. So this is the outburst profile of type 2 burst, and the observations shown here actually show the pulse profiles were changing over time. And by studying these, one can get a picture of how the accretion geometry goes. One can model these pulse profiles to understand the accretion geometry of the system. Of course, power density spectrum is another thing which we can explore, and we can find out what sort of inhomogeneities can occur during these outbursts at different times. So these peaks here in the power density spectrum are related to the spin frequency and the harmonics. While you see in one of the power density spectrum at different intensity, we found these authors, James et al., actually found a QPO causing oscillations. So if you find such features or detect such features in the power density spectrum, one can estimate the magnetic field strength by assuming by simple assumptions of a beat frequency model in this case, where you believe that it's a magnetospheric radius, which is the extent up to which the magnetic field around the neutron star can be felt, is equal to the radius from which the QPO is being originated. So if you balance these equations, one can actually measure the magnetic movement of the neutron star, and hence the magnetic field measurements can be made. Another signatures of magnetic field or way by which we can measure the magnetic field strength of the neutron star in this case is by studying the cyclotron lines in the X-ray spectrum. So the cyclotron lines are also some sort of absorption features which we observe in the X-ray spectrum of X-ray pulsars and give a direct estimate of the magnetic field strength of the neutron star. So coming to the source which we observed, we started with ASTROSAT was J0245. Again, these were the target of opportunity observations made with ASTROSAT, and these are the arrows which shows when the observations were taken. And it's the first galactic ultraluminous X-ray pulsars. Usually, ultraluminous X-ray binary systems are believed to be intermediate mass black hole systems, but there are few handful of neutron stars which have been found to be ultraluminous systems. So they are known as ultraluminous X-ray pulsars or ULP. And it is believed that because of the extremely high mass accretion rates, you observe these superradiantal levels. So I'm not going to go into detail of this. So to point at the study done with pulse files, so the advantage of ASTROSAT was we had simultaneous observations with SXT, which works in a very low band. Then we have LAX-PC, which covers the middle X-rays, and then we have hard X-ray coverage with CZTI. So using one of the high intensity observation with ASTROSAT, we actually looked at the pulse profiles of the system at energies up to 150 keV. We do observe a very strong energy dependence in the pulse profiles. Like you could observe that it changed from single to the double peaked profiles, and then it again comes back to the simple single profiles at very high energies. One can estimate the pulse fraction of the systems. What we observe here that with energy, the pulse fraction is increasing and it can go to very high value, 100% or so. And one can obtain the simultaneous broadband X-ray spectrum. So we observed significant changes in the model components when we observe the sub-Eddington, when the ASTROSAT observation was made below Eddington level and above Eddington level of this particular source. So, for example, say one could get signatures of the optical thickness or optical winds, optically thick winds in the system when it is accreting at very high rates. And those signatures or those spectral signatures were not observed during the sub-Eddington level observations with ASTROSAT. So what we observed with ASTROSAT was one could detect pulsations up to 150 keV, and the changes in the accretion level can actually give an estimate about the subcritical and the supercritical luminosities of the system. Pulse profiles showed strong energy and luminosity dependence, and pulse fractions were also high, and they were comparable to what was observed with NICER and Fermi GBM, which also with NICER also it was like a continuous and dense coverage of this outburst. Our broadband spectroscopy showed significant changes in the spectra between two observations. So as mentioned, optical thick outflows were revealed during the supercritical regime. So I mean, there are models or which are there in the literature to explain this super Eddington accretion of I mean highly accreting neutron stars in ULPs. So it says that there is a presence of the accretion envelope which can lead to the reprocessed X-ray photons, and hence you expect a simpler profiles in the soft X-ray energy band. But if we look at the pulse profiles which we found observed with ASTROSAT, they were not actually very simple in shape. They were not sinusoidal as one would expect in the case of the models being proposed in the literature. This actually points at that this particular type of system, like a galactic ultraluminous X-ray pulsar J0243, could be kind of a link or could act as a bridge between a classical X-ray pulsars and ULP. So we would like to probe into these such systems more to understand what are the changes in the accretion geometry when it accretes at very high levels. Because in the case of classical X-ray pulsars, when they are accreting at super Eddington levels, we observe such complex pulse profiles at soft energies, which is in contrast to what is being proposed in models. So with all this, I would like to say thanks and open for questions.
Thank you very much for this talk. It was very nice. It was very instructive. So we have time for a few questions from the audience. So if there is any question.
Hi, Aru.
Hi.
Can you hear me? This is Tolga. Sorry, I couldn't open the camera.
Sure.
Thank you very much for the talk. Really nice. I just had one kind of comment on the last thing that you said about the bursts, that, you know, NICER, ASTROSAT simultaneous observations are required. They are very much required, but unfortunately, we just couldn't convince the panels since practically the beginning. We've been, I mean, you probably know Manonita, so yes. We've been trying to convince either panels, and each one of them would say, oh, you know, we don't know if you actually acquired enough time from NICER, or the other way, we don't know if you
No, I understand it becomes difficult at times, but if I remember, because I was also part of legacy proposals, and we do have simultaneous observations with NICER and ASTROSAT already.
Yeah,
so, yeah.
It's very bad that they just couldn't have this kind of agreement with the new star that, you know, they could set up a time. There is a little bit simultaneous observations that we could find and actually working on for 1636 and so on. Yes. But yeah, it's a very unlucky thing actually.
Yes, yeah. I mean, of course, it is the most important thing one could probe with two good time resolution instruments in space.
Yeah, thanks a lot for the talk.
Thank you so much.
Is there any other comment or question? So it seems there is no any other question. So
somebody raised hand.
Oh yeah, Şölen.
I just raised hand. I thought this may not be a very particular question depending on actually how much analysis you've done, but in general, maybe this is a more general question in the sense, in particularly in the case of bursts, and you're looking into several bursts and you're seeing some extracurricular unexplained sort of jumps and peaks which are in between bursts and things like that, right? That's what I saw.
Mm-hmm.
Therefore, I was only wondering, have you checked, since you're looking at a large scale of data with ASTROSAT, have you checked how the temperatures of burst temperatures, evolution of burst temperatures in generally behave all throughout long period of time, which means all throughout several outbursts? The temperatures stay suddenly, the temperature in generally, are you also like the burst temperatures that you see, and also the black body temperatures that you see at the burst? And also, are you checking some sort of the temperature of the neutron star itself? So how that compares in long term? That I'm asking you a long-term question, and if you haven't done this, really, you haven't looked at this, that's okay.
So when you talk about long-term, what time scales are you talking about?
Well, actually, I'm not talking about any particular time scale. Several outbursts, let's say.
So when we talk about
outbursts, meaning bursts.
So when you talk about, like, if you're not sure about time scales, so we have done temperature measurements. Let me go back to the slides because I was rushing here. So this is the temperature profile during the thermonuclear X-ray burst.
Yeah.
And when you talk about, so you could see that temperatures can go all the way to 2.5 kV, like close to the decay.
Yeah.
So
okay.
It's a specific...
That's okay. That's okay. But then what happens when you look into several outbursts? That's what I'm bursts.
So these
actually those temperatures repeat themselves, or do they? How much difference do you see? And I'm also wondering, that's the temperature of the black body during the outburst. That's not the temperature of the, can you model the temperature of the neutron star itself?
Yes, one can do that. And it's a very good question. And actually, it's a very, I think it's a challenge for us as of now, because first of all, this thermonuclear X-ray burst study is based upon an assumption of black body emission, which is again, has a lot of uncertainties, which I mentioned. When we talk about the temperature measurements, there have been measurements done and not covering, like, only restricting yourself to 25 kV or so. You can extend to energies above here I'm talking about 25 kV in terms of X-ray spectrum. When we study X-ray spectrum, we actually select data in particular energy band. So you can go, if you take, so not based upon model dependent, but we actually did in the past with BEPOSEX data, not with ASTROSAT. So BEPOSEX was again to have the higher energy coverage. And there we used a different technique, which was not black body spectral fitting, which is based upon some assumptions. We actually took hardness ratio. Now, hardness ratio is something similar to like hard and soft color, which I described previously in my talk. So when you take the X-ray photons in the hard X-rays and soft X-rays and take these ratios, and that we can translate into your black body temperatures. We developed a technique where we could estimate temperatures on those hardness ratios. So using that, we actually studied a lot of, almost all thermonuclear X-ray bursts observed with BEPOSEX, I'm sorry. So what we found was that interesting factor was, like, in some of the bursts, we actually saw a very peculiar temperature dependence of the profiles. And in those cases, the temperatures were very high, which was like above 3.5 kV or so. So normally when we have studied, or we look at thermonuclear X-ray burst profiles, so temperature thermonuclear X-ray bursts are like within 1 to 2.5 kV or so. And again, 2.5 kV or less than 3 kV depends upon what type of thermonuclear X-ray burst you are talking about. So if it's a photospheric radius expansion burst, which is another special class of a thermonuclear X-ray burst, you expect a higher temperature profile. But in those cases, the sources what we studied and profiles what we found was like they were not photospheric radius expansion burst, but still some hard or high temperatures were found, which actually suggests that there could be some sort of a inverse Comptonization effect taking place. Now, this is what we are obtaining as temperatures during the thermonuclear burst. But when you talk about long-term evolution of temperatures, so I assume that you're talking about like after the burst, let's say before first and the second burst, if you look at the persistent profile, we cannot actually model the persistent profile with one black body component. This is you can measure temperature of the temperature of if you are fitting it with a black body plus another component, that will give you some temperature of the accretion disk or maybe the neutron star surface. But then those temperatures cannot like here in this case you measure like a temperature from the thermonuclear surface emission or the emission from the thermonuclear star surface. But in those cases you have to keep in mind that we are now incorporating other emission components also in the accretion geometry. So one has to be mindful in interpreting those observations and comparing directly with those thermonuclear burst. So those observations during persistent emission cannot be used for radius measurements.
Okay, you don't see anything. I see. And okay, I understand. Okay, I got you. And the one thing during the as I see over here in general, okay, so all right, I see. Okay, that's okay, so during the burst, and then there's several bursts here. Okay, okay, thank you. I got you.
Okay.
I see. So there are certain difficulties, and then and you cannot see what happened. So you cannot see it during the persistent emission. So it's not a way you can model.
I mean, one can measure the temperature because you can observe the disk black body measurements or black body emission from the neutron star surface.
Yeah, you don't.
But then you cannot directly relate for the radius measurements of the neutron star, because now you are actually taking contribution from different, because Xa binary itself is a complex geometry because you have an accretion disk, you may have irregularities in the accretion disk, you may have corona on top of that, which is like hot electrons. So all that is contributing to a broadband spectrum. So you have to basically rely upon thermonuclear burst if you want to do mass radius measurements.
Okay, thanks.
Okay, thank you, our speaker again, and for you all for attending this meeting. Then see you next Monday.
Sure, thank you.
Thanks, Aru.
Thank you. Bye. Thanks.
Bye-bye.
Thank you. Bye-bye.
Bye.